Quantum computers will solve science's biggest problems faster than ever before. Scientists have been promising this for the last 40 years, and despite enormous progress, it still seems like a far-fetched dream. So what's taking so long? Basic unit of information in this revolutionary computer is represented by a qubit. Qubits are extremely sensitive to minor disturbances like vibrations or magnetic fields. Therefore, they can only retain their state for a fraction of a second before information is completely lost. So is there a way to make qubits resilient to such minor changes? Say hello to topology. What is this topology? In mathematics, topology is concerned with properties that are preserved under continuous deformation. Let's take this balloon. I can squish it, I can stretch it, or I can turn it back. All these deformed shapes would be considered topologically equivalent. However, if I were to add an extra hole, the shape would no longer be considered topologically the same. Scientists are applying these principles at the atomic or quantum level to study properties of matter which are immune to deformations. We all know our three states of matter, but what if I told you that there are many more states observed at very cold temperatures? How about we do an experiment? Say we have a thin, cold sheet of metal in which the electrons are free-flowing at the surface, and with the battery flow towards the positive end. Applying a strong magnetic field makes the electrons curve to the sides. This splits the charges. The attraction between charges induces voltage. So as we saw, as magnetic force increases, voltage and therefore resistance also increase. So we should expect this relationship to be linear. But this happens. As magnetic field is increased, the amount of electrons curving on the sides is continuously increasing, but the resistance doesn't change until the next spike. So why do we see this? Let's say our electrons are going to a raging party in a multi-story skyscraper and start filling the floor one by one. Each level represents finite energy, and when these levels get completely full of partying electrons, they have to go up a level, and hence we see these spikes and plateaus. Resistance at plateaus is always an integer multiple. This is independent of any dirt, noise, or deformities in the system. Similar to how continuous deformations kept my balloon topologically intact, these robust plateaus are topological states. Further research proved that at high magnetic fields, the surface of the sample exhibits frictionless fluid-like whirlpools of current, or vortices. Due to no friction, they can't be deformed to their original state, which makes them very sturdy. In fact, the amount of rotation of vortices can be described by integer multiples. See a trend? Wait, we just discovered the solution. Two vortices can together form a topological qubit. Information can be processed by braiding and fusing them together. The world around us is full of disturbances and not as pristine as labs where scientific experiments are done. To make the dream of quantum computers a reality, we need technology which is immune to such minor deformities, and topological states of matter are proving to be that holy grail.